Hello and welcome. My name is Kaio and I'm an engineer with Typhoon HIL. Today we are focusing on the new features and improvements included in our latest 2024.2 software release for Typhoon HIL. Join us as we explore more details of what this release has to offer. We are excited to introduce a major upgrade in our time synchronization capabilities, what we call HIL Global Time Synchronization. Previously, time synchronization was restricted to certain protocols and required specific network configurations. However, this update expands and refactors these capabilities, offering more flexibility and broader system integration. Two synchronization methods are now supported: IRIG-B and Precision Time Protocol, or PTP, in which the source of truth for time information is usually obtained from GPS. This information is transmitted either directly or through a gateway, and upon entering the system, it is utilized for time synchronization at the CPU or FPGA levels. This affects all resources and components dependent on accurate timing, including specific protocols, simulation time, synchronization, and timestamping. Given the importance of this feature, we've developed a tutorial video that will guide you through the main idea behind the HIL time synchronization concept, its implementation, and its impact on the system's core functionalities. Once published, you will find the video in the description below. Having in mind what we've discussed before, let's discuss the implications that HIL Global Time Synchronization has on the IEEE C37.118 communication interface. In our library explorer under the communication folder and the C37_118 subfolder, you will find the PMU receive and PMU send components. These components are based on the IEEE C37.118 communication protocol. HIL Global Time Synchronization directly affects the PMU send component. This means that the data transmission performed via this interface is aligned with the system time. Additionally, the time between the transmitted messages is optimized to prevent time drift. All these changes were designed to increase the time precision for components that require time synchronization, including in this case the PMU send component, which exchanges synchrophase measurements. We are confident that the new HIL Global Time Synchronization concept will improve your testing experience, particularly with equipment that requires time synchronization, such as for power system applications. We are happy to introduce two new additions to our communication protocol library: TRDP Publisher and TRDP Subscriber. These components provide support for the Train Real-Time Data Protocol, or TRDP, in accordance with IEC 61375-2-3 standards. With this addition, we aim to provide relevant support for real-time data exchange used in train applications. You can find these new components in the communication folder under the IEC 61375 folder. Let's first explore the TRDP Publisher component. From the component properties, you will see a button where you can select a configuration.xml file to be parsed. We've included example configuration files for each TRDP component in our example library. Once a file is selected, the data is automatically parsed, populating relevant fields with corresponding information. While some of the essential information is shown here, you can see more detailed information about the configuration via the Configuration Preview button. This interface lets you navigate through various tabs and edit parameters as needed. In the Datasets tab, you can access relevant information regarding the expected data types for the component's inputs. This section allows you to verify the array size and ensures that the inputs are provided in accordance with the specified requirements. Notice that the component's inputs have been updated based on the expected datasets. For instance, the first input expects an unsigned integer array with a size of 3. To meet this requirement, 3 SCADA inputs can be configured and interconnected using a bus join component. Next, let's examine the TRDP subscriber component, which follows a similar structure. In its properties, you can also select and parse a configuration file. This action fills in the appropriate fields, which you can update manually if you wish to override any of the values parsed from the configuration file. Similarly, you can click on the Configuration Preview button to bring the interface with extra information. This time, the Datasets tab is where you can find more information about the expected components' outputs. We are excited to introduce an improvement to our 6-phase permanent magnet synchronous machine component. With this new feature, we aim to provide more versatility and fidelity to the component via nonlinear model configuration option, incorporating saturation effect. This component is in the Machines folder under the Synchronous Machine subfolder. Let's check its properties. In the Electrical tab, you now have the option to switch the model type to nonlinear. Currently, absolute inductance versus current is the only available saturation type that can be selected. The remaining fields below corresponds to the values, vectors, and tables used during model computation. They are associated with electrical quantities of stator windings 1 and 2. In this implementation, machine self and mutual inductances, as well as the permanent magnet fluxes, are functions of due and Q components of the machine stator currents. Now let's look at some of the additional features with the 2024.2 release. First, I'm glad to mention a new feature for adjusting sinusoidal sources at a specific phase angle. We will cover that feature in detail in an upcoming tutorial video, which will be linked in the description below. It's time to improve the flexibility of the Profinet component by enabling Ethernet port selection. 4th generation devices were designed with communication interface capabilities in mind, with the HIL 606 offering 4 Ethernet ports and HIL 404 offering 2 Ethernet ports. With this update, we will now find an option in the Profinet component properties to select which Ethernet port you want to use while designing your model for any of these HIL devices. This is particularly useful when you want to simulate various communication protocols within a single model across different networks. The Profinet I/O device component can be found in our Library Explorer in the Profinet subfolder of the Communication folder. In this demonstration, I'm using a HIL 606 device which contains 4 Ethernet ports. As a result, you will notice 4 selectable port options in the drop-down list. Our goal with this improvement is to give you more flexibility for tests that require real-time communication, since this capability is important for concurrent implementation of various communication protocols within the same model across distinct networks. We are thrilled to announce you can now run up to 4 different execution rates per user CPU in 4th generation devices, which include HIL 404 and HIL 606 devices. With this change, we aim to provide greater flexibility and to improve the compatibility with models designed for previous HIL device generations that can support up to 4 different execution rates per single CPU core. To demonstrate this new enhancement, we've created a simple model that includes 10 SCADA input components connected to probe components. Different SCADA inputs are mapped to specific CPU cores using CPU marker components. These markers enable the specification of the preferred CPU core for running the designed signal processing circuit. We have marked 4 circuits for CPU 0, for CPU 1, and 2 for the system CPU. While your user's CPUs have now the improved capacity to handle 4 execution rates, the system CPU is still limited to 2 execution rates. We have set different execution rates for each SCADA input component, making sure each execution rate is an integer multiple of the fastest execution rate within its CPU group. You can find more information about the execution rates across the model by pressing right-click on Schematic Canvas, then going to Visualize Model By, and then choosing execution rates using colors, annotations, or both. We will select both. Now that the execution rates are highlighted, you can also enable the execution rate legend to have more details. Notice that the model contains 4 different execution rates, which provides unprecedented flexibility in model building and CPU resource management. Lastly, if we compile and load this model to HIL SCADA, you can observe the time slot utilization of each CPU. In this way, you can easily track if a CPU core is over or underutilized and distribute the resources more evenly if needed. We are happy to introduce 2 UX improvements that can be used to elevate your experience when designing your model with the schematic editor. First, now you can add a schematic area. To access it, right-click on the canvas and select the Add Schematic Area option. You will notice that the cursor turns into a cross, and by clicking and dragging the cursor, a transparent box is created responsively according to the position of your cursor. When you release the mouse button, the Edit Schematic Area Properties interface appears, and you can add a title and customize it as you wish. This interface also appears when you double-click the shaded region. Let's say we want to highlight the grid part of this converter. Once we've made the box, I can add the title grid to it, and let's also change the color and the font settings. Now, to drag this box, we can click on the shaded part of it, and notice that the non-shaded region is non-selectable, allowing you to freely select and move the enclosed components around. Furthermore, to make things even easier, all the enclosed components can be dragged around simultaneously by clicking the shaded area while also holding the control button. Or you can simply click on this mark on the right side corner. We can resize the box by using the handles on the vertices of the box. Our other featured UX improvement relates to the ability to bypass a component in Schematic Editor. To demonstrate this, let's use this model as an example. Supposing that we want to play around with the model and to check how the compilation and simulation would develop without this core coupling, we will bypass this core coupling. We can do that by right-clicking the component and selecting the Bypass Component option, or by simply pressing Shift-B when the component is selected. Notice that when this action is done, the component becomes transparent and its inputs and outputs are bypassed. Given the way it works, it also means that only components with a symmetrical number of matching terminals on their sides can be bypassed. Once a component is bypassed, it won't be considered anymore during the compilation or simulation phase. Remember that in Schematic Editor you can also opt for the Disable function. This is different from the bypass function since the temporary removal of the component does not conserve the circuit's operational flow, leading to a potential change in the layout or connectivity of the schematic. Since the component is disabled and disconnected, this might necessitate rearrangement or reconfiguration of other parts of the circuit to maintain functionality. If you simply want to remove a component without revising the circuit, the bypass function can be a very convenient way to temporarily remove components from your schematic. Thank you for joining us on this release walkthrough of our latest 2024.2 software release. Your needs and feedback are the driving force behind our continuous improvement, and we encourage you to use these new features in your project and share your experience with us. For more information and updates, stay connected. Thanks for watching.
Check the video description for more resources on this topic, including how to download and get started with Typhoon HIL Control Center for free. You can also visit HIL.Academy to access free courses, expand your HIL testing skill set, and get certified. Subscribe to our channel to get notified about new content.